Chapter 9 begins by looking at the shapes of molecules, applies something called VSEPR theory to determine these shapes, and considers how the shape can affect the polarity of the molecule. Chapter 9 builds on ideas from Chapter 8, in particular being able to draw Lewis structures, account for resonance, and recognize when we have exceptions to the octet rule. All of these ideas and skills are used in Chapter 9. Here I show the ozone molecule. A single Lewis structure does not sufficiently describe the molecule. We have two different resonance structures, and it's the combination of these which then describes the ozone molecule. What does a single Lewis structure fail to account for? Well, if we look at the actual structure, we see that both of the distances from the oxygen atom to the center, from an oxygen atom to the center, they're equivalent. That's best described by a bond order of 1.5. You see that that places a distance somewhere between a single bond and a double bond. Another idea from Chapter 8 was being able to draw Lewis structures for hypervalent molecules. Both of these are examples, and these are ideas that we'll also use in Chapter 9. So let's get started. The Lewis structures we've been drawing and looking at, they're effectively communicating the number and types of bonds that we have, and also the presence of non-bonding lone pair electrons. But they don't tell us the geometry. This molecule here, it might be drawn as if that angle is 90 degrees, but it's not. We need a different way to determine the geometry. And when we consider the geometry, two different features. The electron domain geometry describes where the electrons are found, whether they're in bonds or in lone pairs. The molecular geometry is only looking at the atoms. We want to be able to determine both. So to do this, we need to start with Lewis structures. So here are some simple molecules, CH4, H2O, and H3, BF3. To get started, I want you to sketch the Lewis structures for each of those. And also tell me, is this an easy process for you? What's your approach? Are you using the periodic table? Are you trying to identify the central atom? Discuss your skill with that. These are my sketches for each. In each of these cases, I'm not trying to communicate the geometry. At this point, you're not communicating the geometry, you're just describing whether we have single bonds, double bonds, resonance, lone pairs, features like that. We need a different strategy to begin to describe the geometry. That strategy is going to be using valence shell electron pair repulsion theory, or VSEPR theory. The plan here is to say that if we have non-bonding electrons, single bonds, double bonds, all of those are considered an electron domain. They're placed around the central atom. And the lowest energy arrangement is going to be one that minimizes the repulsions among these different electron domains. And we're going to see that the geometry of the electron domain affects the final molecular geometry. Let's explore that here. This is a linear molecule, whether I was looking at the electron geometry or the molecular. For CH4, there are 4 single bonds. If we spin it around, that's a tetrahedral geometry for the electron domain and also for the molecule. The angles within this ideal tetrahedral are 109.5. If I try to spin it around, it always comes back to 109.5. That is separating those electron domains as much as they possibly can. What if we're looking at the H2O? 2 sets of lone pairs, 2 single bonds. The electron domain geometry is again a tetrahedral, but now that's showing a bent structure for the molecule. This would describe NH3. The electron geometry is again a tetrahedral, but the molecular geometry is called a trigonal pyramidal. If I try to squish them together, it keeps returning to the same shape. The last example, BF3, It is a trigonal planar electron geometry, and the molecular geometry is trigonal planar as well. All of the angles within that, 120 degrees, 120 degrees, 120 degrees. Here's a summary of what I showed within that simulation. We had different electron geometries and different molecular geometries. I'm pointing out that in that ideotetrahedral, the internal angle is 109.5. I think within the trigonal planar, we saw an angle of 120, and that's something you could probably make sense of. So in all these cases, we want to be able to consider how the electron geometry was informing then the molecular geometry. Let's try it with a different molecule. What would be the VSEPR predicted electron and molecular geometries for the central atom in this molecule, Cl2Co? Once again, make a sketch. Is this an easy molecule for you? What's your approach? And then also go on. What do you think the electron and molecular geometries are around that central atom? Stop the video, share your work. Here's a Lewis structure. Both the electron and the molecular geometries are both trigonal planar. Going back to CH4NH3 and H2O, in all cases, the electron geometry was tetrahedral, whether we were talking bonds or lone pairs. The molecular geometry, however, were not all the same. The molecular geometry is influenced by the electron domain geometry. And we see that the molecular geometry also slightly deviates from the ideal geometry when lone pairs are present. It appears that the lone pair is taking up more space than the single bond. And this leads to a slight decrease in the bond angle. How much? Well, in an ideal tetrahedral, they're all 109.5. In a trigonal pyramid, it's down to 107, and in this bent structure, 104.5. So a small decrease from the ideal. What leads to greater repulsion, a single bond or a double bond? This is the structure we looked at a moment ago. Let's look at the bond angles to see if we can find a difference. Here's the actual data. It looks like the double bond is taking up more space. It's squeezing this Cl carbon Cl bond angle a little bit smaller. Recall in the ideal geometry they would have all been 120. In this case, it appears that the double bond is taking up more space than the single bond. Here I show two molecules that have quite a few different angles. What I'd like you to do is estimate the bond angles. Just as an example, this bond angle 1, the hydrogen, oxygen, carbon, it's shown in this sketch as 180 degrees, but it's not. Remember, the Lewis structure is not telling us the geometry. We need to apply VSEPR theory to do that. See if you can estimate all 6 of these angles and which one is closest to 109.5. Give that a try. Within my own work, these would be my estimated values. There's 6 different answers shown. Which ones do you have questions about? So far within the video, we've looked at examples in which we have up to 4 electron domains, and it's led to different molecular geometries. Our plan is that we need to be able to draw a Lewis structure, apply VSEPR theory, be able to name the geometry, estimate the angles, and also use that to determine the molecular polarity. That's another skill for us. Carbon dioxide and H2O, what would sketches of those look like? Carbon dioxide is a linear molecule, H2O is a bent one. If we look more closely in terms of the polarity of the molecule, H2O is being described as a polar molecule and CO2 a nonpolar one. Within CO2, I see bond dipoles, and yet it is described as a nonpolar molecule. Let's learn about that. So within here we have the representation that we looked at before with differences in electronegativity. As we change the electronegativity, it can become more covalent or more ionic. Notice how we are changing the bond dipole. How would we know if it's a polar molecule or not? Well, if we place it in an electric field, we see that it becomes aligned with the negative and positive plates because the molecule has a negative and a positive region. That's how we tell if it's a polar molecule or not. In this case, no bond dipole, it's not being attracted to the electric field. Now let's look at this molecule. We'll see that there's differences in electronegativity which are leading to bond dipoles. And we have partial charges as well. Turning on the molecular dipole, I don't see anything. If I turn on an electric field, I don't see it orienting and aligning itself in that electric field. If I were to change the electronegativity and introduce a molecular dipole, now I see that it becomes aligned. Another way that I can have a molecular dipole is changing the symmetry of the molecule. So this is interesting. I can have bond dipoles present, but as vector quantities, if they cancel, it does not lead to a molecular dipole. So we're distinguishing now between whether we have a bond dipole or the entire molecule has a dipole. A polar molecule is a molecule where one end has a positive electrical charge and the other end negative. CO2, however, is an example of a nonpolar molecule. Overall, it has a zero dipole moment. Even though there are bond dipoles in CO2, as vector quantities, they cancel out. So what we want to be able to do is consider the different geometries. We want to be able to apply VSEPR theory, and with this insight, determine if the molecule is polar or not. That's going to be a key skill for us. That key skill, we haven't practiced it yet for these hypervalent compounds. That's something we're going to work on. Here's two questions that are tied directly to skills that were introduced within this video. Give both of these a try.